Okay. So, as we have discussed in the previous class, that we will be now concerned about a signal which is non-periodic in nature. Most of the signals, if you see, we have defined periodic signal, and the fundamental property of a periodic signal is that it must be defined from minus infinity time minus infinity to plus infinity. That means that periodic signal must repeat at some interval, let us say t0, which is the fundamental interval, and it should go from minus infinity to plus infinity, otherwise that periodicity will not hold good. Okay. So, but most of our signal actually start at a particular instance, whatever practical signal we can see, suppose a voice signal generated by me, it will start at a particular time instance and it will end at a particular time instance. So, they are finite in time, they cannot start actually at plus infinity minus infinity and cannot go extend up to plus infinity. So, most of our real life signals are time bounded. Okay. So, therefore, they have a finite energy, because if you go from minus infinity to plus infinity, you will probably if you wish to evaluate power, you will see probably it is 0, okay, because the signals are not stretched up to minus infinity and plus infinity. So, our signals are generally energy signal, that means it is time bounded, it starts at a particular time and ends at a particular time. So, we should have a strong analysis of those kind of signal, otherwise our analysis is not true. So, whatever Fourier series gives us, that is a very strong tool, we can agree on that, but still that particular thing is not good for real signal. So, we need to have good understanding about the real signal which are finite in time. Okay. So, let us try to take an example. Let us say a very simple example signal which is defined as Gt. It starts at some value of t, let us say a, and it ends at some value of tb. So, this is the time. So, with if this is my present, let us say 0, time 0. So, this was my past at which time some value a, which is negative in time, it has started and it will end at b. So, that is the future of the signal. So, this is the signal. So, it starts at a, it ends at b. If this is a signal and I wish to still do similar analysis as Fourier has done in his Fourier series analysis, right. So, I still want to see what are the frequency component it has, how to define them, can we get some spectrum out of it, all those things. Okay. But the problem is, whatever Fourier has done, that was good for periodic signal. So, what we will try to do, or what Fourier has also done, that for a periodic signal only we have some strong result. So, can we apply those result into this? So, for that we have to forcefully make this signal periodic. So, let us try to do that. Let us say beyond this we define some amount of time, that is our period, okay, and the same signal is repeated at every t0. So, basically what happens, if this is t0, my signal was like this, after another t0 there is another period of t0 where the same signal is repeated, and there also it repeats and it gets stretched to minus infinity to plus infinity. So, basically from our signal which was defined from a to b, we have created a period which actually takes into account this a and b inside that period, and then we start repeating this signal. Whereas, in the original signal there was nothing beyond a and b or beyond even this t0, but we have deliberately made this signal looks like a periodic signal. Very nice. So, this is a newly constructed signal from that original signal. We call this as G T0T. So, that means from this signal we have transformed into a periodic signal, right. But the good part is, by means of this clever construction, we can always say, if I take this limit t0 tends to infinity g t0 t, that exactly goes to gt. This was what we were targeting. So, we were actually trying to see a particular signal, can that be represented as a special case of periodic signal. Okay. So, we have constructed that particular signal, and then we have told, okay, now if we stretch this period to infinity, okay, or this T0 to stretching from minus infinity to plus infinity, then definitely these parts will not appear. So, they will disappear because the period gets stretched up to minus infinity to plus infinity. So, that will exactly look like our GT. So, this is what we are now targeting. So, what we are targeting is deliberately we are making a periodic signal out of a non-periodic or a energy signal which is time bounded. So, this is something we have done. Now, for GT0T, which is a periodic signal, I can do Fourier series analysis. So, for GT0T, which is a periodic signal with period T0, I can always do a Fourier series analysis. So, n minus infinity to plus infinity dn e to the power j n 2 pi f0 t, I can write this way, where this f0 is 1 by t0, the period I have constructed, the frequency, fundamental frequency is 1 over that. Okay. So, this representation is true, I can always do a representation like this. And after that we have to evaluate dn. So, dn is something we already know, it should be 1 by t0 and integrated from minus t0 by 2 to plus t0 by 2 over the period g t0t, which is the main signal, and e to the power minus j n 2 pi f0 t dt. So, this is something we already know, right. Very good. Okay. Now, let us see what happens to our representation. Okay. So, in our representation, let us try to do it this way. Let us define, we are just arbitrarily defining for our, you will see why we are defining this. So, let us define a GF, which is nothing but a integration from minus infinity to plus infinity GT original signal e to the power minus j 2 pi f0 t dt. We are just defining this. Okay. This is our, by definition we are saying that because this, sorry, it should be on the f, because this is a integration over t. So, the t will vanish, it will be a finally a function of f, we are defining that as a capital GF, a function of small f, right. So, this definition is correct, no problem in that, as long as this integration can be done. So, if we can, if we say that this integration is possible, we can always say there will be, this will be a function of f, because t goes away, right. So, we can write that function as some capital GF, some function. Okay. So, this definition is correct. When this definition is correct, what I can write about dn? So, let us see what is dn. So, now this dn, if you carefully see, this dn has 1 by t0, that is all right, and in place of gf, if I just write f0, okay. So, if I just write f0, then what will happen? I will be getting this gt integration minus t0 by 2 to plus t0 by 2, and I will have e to the power minus j n 2 pi. See, the similar things are there, just in place of f I have a f0, right. So, basically what I can say, this particular part, if I put t0 tends to infinity, okay, immediately this limit goes from minus infinity to plus infinity, and as long as I say t0 tends to infinity, my g nt, if you see the previous definition, sorry, g t0 t, if I put t0 tends to infinity, g t0 t I can write as gt. So, I can write gt and replace that as g t0 t. Okay. So, I can, if I say that whenever I will put this particular limit, I will be always getting this representation as if g, in place of f I will be putting f0. So, this is quite obvious, as you can see. What is gf0? Gf0 will be just replace over here gf0. So, that should be gt e to the power j 2 pi f0 t dt. Okay. Only problem is we have a gt over here. So, gt as long as t0 is tending towards infinity, which is this case, gt and gt0t are similar. So, I can replace by gt0t. Now, if you go over here, now this to limit t0 tends to infinity means minus t0 by 2 and plus t0 by 2 goes to minus infinity and plus infinity. So, I can replace this to limit as if going to minus infinity to plus infinity. So, therefore, dn exactly mimics these things. Okay. So, that is the beauty I could do by this definition and by our definition of gt and gt0t, or the relationship between these two. Okay. So, once I could do this, I have got a very nice construction. So, what is that construction? Now, I can see that what happens to my dn, dn becomes 1 by t0, which I have already written, this is my dn, and immediately I can represent my gt0t, which is a Fourier series expansion. So, which is summation n minus infinity plus infinity dn e to the power j n 2 pi f0t, and in place of dn if I can replace this. So, it happens to be n minus infinity plus infinity 1 by t0 g f0 e to the power j n 2 pi f0 t, right. This is what I get for this particular part. Okay. So far it is all good. Now, let us try to see what does this particular thing means. Okay. So, what is happening in this case, we have already assumed, otherwise we could not have constructed this dn equal to this, that t0 tends to infinity. So, whenever t0 goes to infinity, I have a relationship f0 equal to 1 by t0. So, what happens to f0? f0 tends to 0. Okay. So, this 1 by t0 or f0, I can, that becomes infinitesimally small. Okay. So, that becomes infinitesimally small. Instead of writing it as 1 by t0, I can now write as del f, where this. So, I am just replacing f0 equal to del f, which tends to 0. It is just for my convenience, because we are used to see del f, and this is g f0, or sorry, let us see, is it g, there is something that we have missed here. So, it is n f0 which makes the f. So, it should be written as n f0, right. So, that was the mistake we did. Okay. So, because it is if you see the construction, gf is written as gt e to the power minus j 2 pi f t. Now, here in the construction we have e to the power minus j 2 pi t, all are there, and n f0 is there. So, therefore, it must be n f0, right. So, that is all right. So, this should be all replaced by n f0. Okay. So, del f n f0 must be replaced as n del f, right, because f0 is replaced now by del f. So, g t0t, newly constructed g t0t becomes summation n equals to minus infinity to plus infinity, 1 by t0 becomes del f, g n f0 becomes del f e to the power j n f0 becomes del f 2 pi t, right. So, this is the new construction that we have got for g t0t, and we know here t0 tends to infinity and del f, which is 1 by t0, goes to 0. Okay. So, this is something we already know. Now, let us try to see what exactly is happening. What is this part? This was some function gf. Okay. Now, whenever we start varying this n minus infinity to plus infinity, so what is happening? Whenever n is equal to 0, so it gives g0, n equal to 1, it gives at del f whatever value of gf. So, this must be g only del f. So, this is g 0 at n equal to 2. So, this is at n equal to 1, n equal to 2, it gives me g 2 del f, and so on, and also so on in this direction. So, basically it is almost like there is a function gf which is a continuous function, and whenever we are putting this different values of n, we are actually sampling this function at del f interval. Now, as long as this del f is becoming infinitesimally small, so what is happening, all these samples are coming closer and closer together. Okay. And in the same method, what is happening to this particular value? So, this is nothing but, suppose I have a gf, let us say this gf looks like this. I take, suppose n equal to 0, I take this value and I take this box. So, what will be the area under this box? That should be del f into g 0 or 0 into del f. The next part will be again del f, and what is this value? This value is g 1 into del f into del f. So, it is almost like this small boxes, I am actually taking the area under that, okay, and I am adding all this. Once I do summation, I am actually adding all these things, right. So, as long as my del f tends to 0, what is happening, this summation almost becomes integration, because integration also gives me area under a particular function. So, if I just now think that my overall function is this particular thing, that is gf into e to the power j 2 pi f t, where f is replaced by n del f. So, basically what is happening, this particular function I am adding with, or I am multiplying with del f, and I am summing it up whenever we put f as discrete values. So, it is nothing but this summation becomes integration, and my g t 0 t just happens to be a integration, and because it goes from minus infinity to plus infinity, whenever we put n equal to minus infinity, what happens, this n into f 0 goes to minus infinity. So, if my variable is f, that goes to minus infinity, and whenever I put n equal to plus infinity, it goes to plus infinity. This del f becomes df, and I have this gf e to the power j 2 pi, this is replaced by f t. So, basically n del f is almost becoming a continuous variable f. This is very true. We have already stated that if del f is small, then all the values I am taking almost becoming continuous in time, in frequency. So, basically I was taking, initially I had this function which is gf into this, I was sampling that function and I was trying to calculate the area under it, because I was multiplying by del f and taking that box and I was adding all those things. So, this is nothing but integration, that we have already understood, and what is also happening, I am making this del f smaller and smaller. So, those samples are coming closer together and getting very closely packed, and actually those samples are almost indicating now a continuous variable on f. So, whenever I write n del f, that goes to f, okay, where the f varies, that becomes the integration variable. So, immediately I get this, and because my t 0 tends to infinity already for this construction, so this can be written as gt, because gt and gt 0 t becomes equivalent as long as t 0 goes to infinity. That was our definition of the signal. So, we made this aperiodic signal to be periodic with period t 0, and then we have told that this t 0, if we stretch to infinity, it becomes a similar aperiodic signal. This is something we have already stated. So, as long as t 0 goes to infinity, we get this very nice relationship. So, what has happened, now we have a two relationship that we have said. One was our original statement that gf must be related as this. This was by definition gt e to the power minus j 2 pi f t dt. And now from the construction we have got another relationship where we say gt is nothing but minus infinity plus infinity gf e to the power plus j 2 pi f t df. So, this is the famous Fourier transform and Fourier inverse transform theorem you can immediately identify. Okay. So, if I have a signal gt, I can always get a corresponding Fourier transform which is gf, and if I have a signal means if I have Fourier transform, I can always do an inverse transform to get my signal back. So, this is the Fourier transform and inverse transform. In this whole process, the most important part is this gf, which is intermediately constructed. So, what is this gf? If you carefully see the construction, this gf is actually almost similar to, as you have seen, it is almost similar to our dn. We have derived this earlier. So, basically we have already stated that dn must be 1 by T0 into G n del f. Right. What was our dn? Dn was for every frequency component the corresponding amplitude and phase. Dn was giving me that. Now, G, if as long as del f tends to 0, this becomes a continuous variable. Okay. So, this n del f, as long as del f is very small, this almost becomes a continuous variable of f. So, this is nothing but our T0 into dn, or I can write this dn equal to this. So, basically what is happening, the corresponding dn can be calculated if I know that gf, whatever that gf is, and I multiply that with that very infinitesimally small frequency component del f. So, what is happening? Suppose I have a particular, let us say a Fourier transform representation gf. Okay. So, each one of this for a particular value of n are actually representing, suppose this is my gf, right. So, that sample value, if I multiply that with del f, so this area, okay, or let us say this area, so gf multiplied by that del f, this area as if giving me this dn. At that frequency, what is the overall coefficient of that frequency component? So, what is eventually happening, as I put this del f tends to 0, very small and small, I am actually getting all frequency component. So, it is almost becoming continuous. Earlier in my periodic signal, I was only getting those harmonics, so f0, 2f0 and all those things. Now, for a periodic signal, what we have observed that, because for that aperiodic signal, we have represented it with respect to a periodic signal. So, if we faithfully represent back the aperiodic signal, T0 has to be infinity. Once T0 is going towards infinity, this del f is becoming very small. So, that means it is now almost those frequency components are getting closely packed. So, we are getting almost all the components, all the frequency component in a continuous domain, right. And everywhere if I multiply by this del f, that gf whatever I have, if I multiply by this del f, I get the strength of the frequency component similar like this dn, right. So, what might happen? Suppose in a hypothetical experiment, I keep on, because I have to go means stretch my T0 towards infinity, I keep on reducing my increasing my T0. So, earlier suppose this was my representation, okay. So, this was my del f. Now, what I do? I actually increase my T0. So, immediately what will happen? If I increase my T0, so immediately this will, suppose I make T0 double. So, if I make T0 double, immediately what will happen? this dn value, because T0 is doubled, dn value will be reduced by half. Okay. So, what happens? Dn value will be reduced by half, but the samples will be now more. So, basically instead of this, it will be all reduced by half, but the samples will be closely packed, double closely packed, because del f is now becoming half of the previous this one. So, they will be double closely packed, and the sample values, which is represented as dn, which is the integration or we should say which is the area multiplied by del f g n del f. Okay. So, that area is represented by these values. So, they will be becoming half, because I have increased my T0 to double, correspondingly my F0 has become half. So, basically sample will be, there will be double samples now, more closely packed, but their strength will be reduced. And if I keep on doing this experiment, what will happen? I will still get these samples, but their values, as long as T0 goes to infinity, their individual values will go to 0. So, basically what I am getting at every point in continuous frequency domain, I have some value, but the corresponding value is 0, because T0 goes to infinity. Okay. But the relative values are still being constructed by this GF. So, however small you make them, they have a relative nature. So, if this is the strongest one and this is little weaker, they will still remain the same, their individual value will tends to 0. Okay. But their relative nature, which is captured by this GF, will still be the same, and that characterizes the corresponding signal, the relative nature, but individual values at a particular frequency is no longer existent. This is a very typical there is a typical understanding behind this. So, probably we need to have some clarification. One very simple example, which is often used in probability theory, probably you will have better understanding. So, suppose I have a pivoted rod and I give a random force to this rod, and this rod can freely rotate around its axis, and depending on that random force, it will go and stop somewhere. Okay. Let us say where it stops. So, let us say it stops over here. That angle is called theta. Now, this theta becomes a random variable. Okay. Now, if I just ask you that, can you tell me the probability that it will stop at angle 30 degree? Now, how many possible angles are there? Suppose the force that I will be exerting are almost the way it is being exerted, that whichever angle it will stop, they are all equally likely. So, it has equal probability of stopping to any angle, right. So, if that is the case, every angle is equiprobable. So, they are equally favorable. So, now I am targeting a particular angle 30 degree. Okay. So, how many angles in between are there? There are infinite number of angles, because 30.1 is a valid angle, 30.01 is a valid angle, 001 is a valid angle. So, there are infinite number of angles. So, the favorable case for my that 30 degree is only one, that it should stop at exactly 30 degree, 30.0000 up to infinity. Okay. But there are infinite number of possible cases. So, my probability, that frequency definition of probability, will give me just 1 upon infinite, that is 0. So, stopping at a particular angle is 0. Okay. So, it does not have any probability of stopping at a particular angle. But if I now specify a angle range, let us say between 0 to 90 degree, it will stop, because things are equally likely. Now, let us try to see, it has 4 quadrant, so it has almost 360 degree. Out of that, I want to cover this 90 degree, right. So, that must be my probability, which is 1 by 4. So, whenever now I am specifying a range, I have a valid probability value, whereas if I specify a single value, I do not have anything, no probability values are recorded. Same thing happens to this GF. Whenever we are talking about GF, I plot a GF, individual value I do not get anything, but if I specify a range from frequency f1 to f2, it has some value, because it will be the integration over that and I will get some value. Any function, if dn is the way dn is defined, if you see, dn is the strength at a particular frequency. Okay. So, if I say from this frequency to that frequency, in Fourier series term I will be just summing all dn. Okay. So, from that particular frequency to another frequency I will be summing all this dn, whereas in this particular representation, if I have to sum dn, what I have to do, the summation becomes integration. We have already seen that dn was nothing but that del f into, so it is area actually, del f into g whatever that n del f, right. So, basically, and then summing over that n value, whichever n value we are targeting. So, f1 to f2 will have some n value to some n value. If I am doing this, it is just area and we are summing that, it just becomes in a continuous variable, that becomes the integration from f1 to f2, I am integrating it. So, basically what is happening, whenever we are saying that an individual value, that does not exist, because del f tends to 0, this area tends to 0. So, I do not get a value, but if I start integrating from a particular frequency range to another frequency range, I get some value. Okay. So, that is the beauty of it. In the next class probably we will again discuss what is the implication of this thing.